I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism Podcast, an exploration of the past, present, and future of material science. My name is Taylor Sparks, coming to you from the University of Utah's Material Science and Engineering Department, and I'm joined, as always, by Andrew. How you doing, man?
Doing pretty well. It's been a good semester, and I think we have a really good episode today. It was really awesome going through the literature and learning all about it, and can't wait to talk about it.
Oh, absolutely. Today we are talking about bulk metallic glasses. Now, I know what you're thinking. I'm familiar with glasses, but bulk metallic glasses? What are those? Well, we're going to tell you all about it. But first, let me just say that these aren't that old. They've only been around for like 60 or so years, and the design space where you can find these things turns out to be pretty massive.
They estimate that there are about 20 million different compositions of bulk metallic glasses out there. And if we were using traditional scientific methods, the tried and true, that would take probably about 4,000 years to do.
So that's not going to work. It's a good thing that we don't have to rely on that we're basically living in the future. We've got robots, we've got machine learning. There are ways to explore big design spaces efficiently, and there's a company that's willing to take this challenge on. Radical AI is the sponsor of today's episode, and we will have a lot more to say about their cool approaches to materials discovery in future episodes. But we figured we can't dive into that until we first tell our listeners the basics of bulk metallic glasses. What are they? How do they work? Why do we care about them? Why is it worth going through this effort to find new ones? So to do that, we are joined by a fantastic expert in this area, Jan Schroers. You want to do an introduction for yourself, Jan?
Sure. So thank you very much for having me here. My name is Jan Schroers. I'm a professor in the School of Engineering in the Department of Material Science and Mechanical Engineering at Yale University. I've been here since 2006, and before I have worked at a commercial company actually working on commercialization of these materials. And so I have been dealing and thinking about these materials for 20 plus years.
I don't think I knew that you worked on bulk metallic glasses before coming to academia. That's fantastic. What a perfect person to have the perspective on this then.
Thank you. Yeah.
Well, maybe to kick it off, can you tell us what even is a bulk metallic glass? What are these classes of materials? A little bit about their history maybe.
Yeah, so a bulk metallic glass is nothing else but a liquid metal that upon cooling has no chance to crystallize, right? So if you think about most metals, right, essentially all metals that you are familiar with, when you melt them and then subsequently cool them, and when they solidify, they typically crystallize. They do this because the crystalline state is a better compromise of order, and order is more important at lower temperature. That's why at low temperature things are typically crystals. At higher temperature they are liquids. At even higher temperature they are gases. Right. So that's why typically metals crystallize. Right. However, for them to crystallize, it takes time. Right, the atoms, they have to slightly change their positions, sometimes even significantly change their positions, depending on, and that's where we will get to a little later. And so this process requires a time scale. And if you cool them now faster than this time scale, the liquid cools, gets to a lower temperature, has less thermal energy, moves slower,
Just
and
frozen in place.
It wants to crystallize, but it loses its ability to crystallize. And then it freezes into a glass. And so that's true for any glass. And if you do it with a metallic liquid, a melt, then that's called a metallic glass. So
okay.
It's a frozen in liquid.
So this should sound familiar to people who've studied material science, because even in an introductory class, you learn about the kinetics of nucleation, right? And they introduce the idea of these time-temperature transformation diagrams. Maybe I'm bringing back PTSD for students who saw this, right? where you have to avoid the nose of that diagram. And if you do it fast enough, right, if you can quench it quickly enough, in that case, we're usually talking about, say, austenite steel transforming to pearlite. But you're saying that it can go from the liquid state and avoid crystallization altogether. It's not just in the common materials like silicon dioxide, right? We make, fused glass and things out of that. But you're saying you can do it even in metals, which are much simpler structures. So I imagine you have to cool them a lot faster to prevent them from nucleating.
Exactly. And this is why it took so long, right? So even in natural processes, silicon dioxide can form easily glass, whereas with metals, this has never been observed. And that's why it seems such a crazy thing when it was first reported, right? They're very simple. Their units are atoms. And the nucleation barrier is very small, right? And the kinetics for nucleation is very small. And so if you try to quench a pure metal, let's say gold, a liquid into a glass, it is very, very, very difficult, right? Because you have to stop so all it takes to crystallize for these liquids is less than an atom movement.
Super small shift, right?
And this happens extremely fast. So the cooling rates are impractical. And the key about metallic glasses is that, and particularly about bimetallic glasses, is that we learned this and slowed down the process of crystallization more and more and more. Hence, it gave us more and more time to cool them. That's really the main design criteria to make them easier to achieve.
The word I kept seeing over and over again in the literature is this idea of frustrating the formation of a crystal by adding multiple elements, elements with very different sizes, things that are going to obstruct and maybe just give you a little more time to cool past that crystallization point.
Yeah, and as the structures get more and more complex, one of the points I saw was that the actual energy stabilization relative to amorphous, it gets smaller. And so the driving force for that crystallization is also reduced. Now, Jan mentioned that, he talked about gold as a candidate system. I'm glad you brought that up because in reading about this, I saw that was the first one, right? This was the first example of a bulk metallic glass was in the gold silicon system, which I remember teaching my intro to material science students because it is a good example of a deep eutectic, right? Pure gold, pure silicon really don't tolerate much of one another. They're basically immiscible entirely. There's very little, if any, solid solubility. And yet there exists this eutectic point which dives way down in temperature. I think it's 300 something, 360?
Yeah.
360. Yeah, so very, very low. So this makes sense. Here you have a mixture where you've got a mixture of, I don't remember where it happened, the eutectic's probably 20% or something like that. Mm-hmm. But you've got this mixture of gold and silicon. And then all of a sudden at a low temperature, so diffusion's not going to be very high, you have to somehow eject out all the silicon and eject out all the gold to separate regions. And that would give you the eutectic structure. But that takes diffusion. And if this is happening so fast at such a low temperature, it just won't happen. And so you're left with this frozen sort of structure.
Exactly. Yeah. That was the main idea by Paul Dewey, who is often credited as the inventor of metallic glasses or the discoverer. I can say a few words about this whole thing maybe
please,
in a minute.
I'd love to hear it.
But that's exactly the idea, right? So the time scale, if you take a pure element, is essentially they buzz around with a frequency of about 10 to the 13 hertz, right? And so all they need to do is collectively buzz and form something that looks like a crystal, and that leads to crystallization, overcomes the nucleation barrier. If you do what Paul Dewey did, you take gold and silicon, at gold 80, silicon 20 roughly, then the first of all, the liquid becomes very stable. So gold, like silicon, right, even though it seems ironic, in solid form, it spits out all the silicon. Yeah. It doesn't tolerate it. But in the liquid form, it very much likes silicon. This has to do in the solid, the atoms, they're confined to a lattice. And even though they like each other, but the lattice is so distorted that they cannot tolerate each other. So what happens then is the liquid becomes very stable relative to the solid. That's why the eutectic is so low, right? Gold melts at 1060, silicon 1400, but the eutectic goes down to 360 degrees C. It remains a stable liquid. So you just have to bring it a little below this, and then it becomes so viscous that yes, it wants to crystallize, but the kinetics, right? And this is the Stokes-Einstein equation that correlates viscosity and diffusion. So the kinetic is so slow that it is much, much easier now to form a glass, right? Or much harder to crystallize.
And this was only 60 years ago. This isn't like, one of the things that's so fascinating about material science is that a lot of these amazing materials that are all around us, whether it's PVC invented in the 70s, right? It was basically a generation or two ago. These weren't that long ago. And I guess around these early days, 60s, 70s, there was a lot of work in similar systems. They took systems that were a lot like gold silicon, and they found a few other members. Do you want to talk about the early days of this and what was happening?
Sure. So as I said, even though Paul Douay, who's a Belgian-born scientist who works at Caltech in California Institute of Technology, he is credited to have discovered these materials, right? They have been, the first clearly reported work was about 6 years earlier in Germany, in Göttingen. Buckel and Hilsch, they did something quite similar, right? But they used tin vapor and in this tin vapor, they put a very cold piece of copper that's water cooled, right? So then the vapor condensates and it goes essentially from the gas immediately into the solid. And they reported the first amorphous metal, right? And there's even earlier work that is it's almost mystical. So Russians claimed they have done this about 5 years earlier, and it's only published in a Russian journal. So I can't really, I heard it from many sources, but I've never really, looked through this report. And the other kind of ironic thing is they weren't interested or even thinking about metallic glasses. They wanted to make microstructures with smaller and smaller and smaller grains. So that was already understood. The smaller the grains in the microstructure, the stronger they become. This is the so-called Hall-Patch relationship. They become smaller and smaller and stronger, and they were envisioned, okay, let's push this to the limit. And they were very surprised. In fact, it took quite a while to convince the scientific community that these are not nanocrystals. These are they're very different materials, right? So that was in the 60s. And then about 10 years later, Turnbull and Chen, two researchers at Harvard, they got the idea right away, this what you just talked about in gold silicon, that you have this deep eutectic, and thereby the liquid becomes very stable at a 360 degrees C relative to the solids, right? And so they pushed this idea further and further, and they focused on, and it's a completely coincidence in palladium. So palladium forms these really deep eutectics with silicon,
nickel,
with boron, and also with nickel, and or they're helpful there, right? So they discovered the first bulk metallic glass in 1970, which was palladium copper silicon. And bulk metallic glass is just referred to because before they had to be very thin, right? We talked about beating this time scale of crystallization. And the way, of course, you beat them, you have to take the heat out very quickly, right? So you have to cool them very fast. And the thinner the sample, the shorter the diffusion path for heat is, and the faster you can cool them. So they observed that even if they make samples in bulk form, which they arbitrarily defined to be 1 millimeter, they said this is a true bulk. So even for these very thick sample, or in other words, for very long times or slow cooling rates, they can form these glasses, right? So that happens in the 70s, right? And
really quick, you mentioned different timescales, slow versus fast. Can you give us a sense of what that means? Like how many degrees C are we changing per second to try to bring the heat out?
Yeah, very good. So if you take a pure metal, this is on the order of 10 to the 14 Kelvin per second.
Insane. Like,
right?
There's a reason why that's very, very difficult to achieve.
It's very, very difficult to achieve.
I mean, even
right?
gold silicon, right? I think that one achieved basically 1 million K per second, right?
Exactly.
And that's like that's the first easiest one they found, and that's still really hard to do.
That's still really hard to do, and you can, therefore, gold silicon you can make about 50 micron thick, right? So to remind you, the human hair is something like 150 micron in diameter, right? So not very thick. The pure metals are very, very difficult, and there's only really academic examples, right, where there's indication that they can be formed. So that's the time scale. And now if we go to the best metallic glass formers, they can be cooled with cooling rates down to 10 to the minus 2 seconds per Kelvin.
That's incredible. That's incredible. You have so much time to accomplish it.
Yeah.
So all of a sudden you can start making bulk materials.
Yeah.
So I'm guessing that in this sort of looking at the timeline, okay, they were able to make it, but it was so small. I don't know what types of properties they were measuring on the very first ones. But at some point it's getting big enough that they can measure properties. And that's when I think a shock sort of comes to the community. They realize like, well, first off, not only is this a cool new phase of matter, metallic amorphous glasses, but they have some pretty remarkable properties that emerge, right?
Yes. So that's exactly the first thing that happened. In fact, they weren't, because they were based on palladium. And it seems this is like a really like, people always associated this. So palladium is very expensive. It's comparable. Well, these days it changes a lot. It's a little cheaper now than gold, but it kind of right? It's compare ballpark like gold, right? So on the order of like $20 a gram, right? So you will never be able to make something of significant size out of these materials. So the focus has really been on the academic community, that they, for the first time, I mean, one thing that is quite remarkable in physics is people have a very good understanding of this crystalline state. This is, in fact, the state we understand the best. We know where the atoms are, we can see them, we manipulate them, all
Defects,
this, right?
Yeah.
We understand the gas state pretty well because it's essentially isolated atoms, right? The liquid state is the state that is the most challenging state to understand, right, for physicists up to this date, right? And the idea, of course, of metallic glasses for physicists has always been, now we have a liquid, right? It's still a liquid. It just doesn't move that quickly. So it doesn't solve all the problems. It doesn't allow us to do diffraction and things like this to learn about the specific locations of the atoms. But it is very slow, and we can study these things, right? So this is exactly, as you said, has happened, right? They measured these kind of structural properties. They measured the viscosity. They measured this glass transition that has been in our head as we started the broadcast. You cool the liquid, and the liquid moves slower and slower. The liquid has a metastable equilibrium, meaning it's kind of safe in there if you don't get out of this and crystallize it, right? And reconfigures, and at some point it freezes into a glass. It means it can no longer reconfigure. It just stays in a configuration from a higher temperature, right? So they could, for the first time, measure this and looked at different structures and could determine something, connect a little bit diffusion and viscosity and the very fundamental kind of like understanding we have about liquids. A lot of them came from these early studies, but they were always they did not really consider these materials for any technological applications.
Was that just because they were too expensive? But, you know, shortly thereafter, I think we're still in the maybe early 80s now, they started to find non-noble metals, right? That they could make these things out of zirconium, copper, nickel, aluminums, things like that, were all of a sudden at least feasible from a cost perspective to start making things out of them. And within 20 years, at least when you were working in the industry, sounds like they found a way to commercialize them. So what was so exciting from a commercializing aspect? Like, what was the killer app property, right, that was driving their use?
So they were in the 90s. Then the big breakthrough came out of Akisha Inoue's lab in Sendai, Japan. he discovered metallic glasses that are based on zirconium, on lanthanum, on magnesium, right? And then later on cobalt and iron and so on, right? So these are very practical elements, right? They're used in structural applications. And then you could also make bigger samples to mechanically characterize them, right?
Yeah.
They were also easier to make, even with lower rates. So you could make macroscopic samples, mechanically characterize them. People discovered they have very unusual mechanical properties, these materials, right?
Like really high strength at really high elastic limits, right?
Exactly. Yes. Right. So the major difference, and I should say people often are surprised, if you see a metallic glass, it looks like if you take a titanium-based metallic glass or you take a piece of titanium or Ti-6-4, they look essentially the same.
Yep.
Right? But if you put them under a microscope, your eyes pop out. Or if you mechanically characterize them, they are very, very different, right? Because in crystalline materials, you always have these dislocations. These are imperfections to the crystalline structure, and they define the plastic properties. And they're absent in this amorphous structure, right? There's no dislocations. There's no grain boundaries, and all these things that we have learned, right?
It turns the field on its head. Like, how do you describe its properties without that traditional approach? My favorite example is we have this demo that I do for my introductory material science class. It's called the atomic trampoline. Maybe you've seen it, Jan. I'm guessing you have, right? So it's two metal plates. One of them is regular steel, and one has the bulk metallic glass, a couple millimeter thick layer on the top. You drop a marble onto both simultaneously inside of a glass tube, so you can see how much they bounce. And the one that hits the steel, I don't know, 3-4, and it duds out and it's done. And the atomic trampoline, it goes for I don't know. I've never let it go the entire time because basically the energy that would have gone into denting the material, which is, right, there's energy conservation that goes into heat and sound into denting that material. Since there's no dislocations and there's no crystalline structure to easily deform it, you don't get deformation. That energy has to go somewhere. It rebounds. And so these things will bounce for like a silly amount of time. They just go and go. Which you could all, and I love to ask my students, well, what kind of applications could you come up with? And eventually somebody's smart enough to say like, what about a baseball bat or a golf club? Which is exactly, I think, some of the places where we're finding applications of these things, right?
Exactly. The first application of these bulk metallic glasses were golf clubs, right? So for this, people looked at this and said, this is what you want in a golf club, right? You want all your energy of the swing to be translated into in the golf club. And they made them. Liquid metal technology made them. They were later also made in Japan. And then a year later, they were banned. Right?
Oh, really?
So no longer allowed.
They were too good.
They were too good.
I believe it. The demos, it speaks for itself. It's too good.
And so they are only allowed to be used if you put an artificial damper on it, right? So
then why bother?
Right? Why bother? Exactly. Right? So that was one very kind of obvious early on application, right?
Are there applications now, though? Like, where do they actually find use, these things?
Yeah. So the applications that are related to these mechanical properties are in fields like robotics, space, and so on, where you essentially want to utilize these mechanical properties, right? Elasticity is a big thing, right? So for living hinges, for example, right, where in the past, right, robotics is all about moving things, right, and actuating things and so on. So living hinges is a wonderful thing you can do with metallic glasses, which we are all familiar on our shampoo bottle, right? This is one that's a living hinge. It's like a plastic. It's easy to make in plastics. We're very familiar, but we don't have them in metals, right? Because metals are not sufficiently elastic. If you want to make them elastic, you have to go extremely thin, and then they're not strong enough even for this. So that would be one application where you see them.
I just had to Google what a living hinge was. I see exactly what you're saying now, though. You would have fatigue.
Dislocation pilot.
Yeah, if it was plastic, you'd have fatigue eventually, and these things would break. But if it's purely elastic, then you wouldn't have this issue.
Yes. Yeah.
Springs also seem like a good application for these, just with their really wide elastic limit compared to metals.
The resilience you can store into that is huge then.
Exactly. In springs, you see them. In fact, the watchmaking industry has been very interested in these materials, right? A lot of this has to do with casing, which is different, where we can talk about it. These are actually the major applications of these materials, electronic or component casings. But they have looked into the mechanical, right? The mechanical battery of a mechanical watch, right? The so-called mainspring. It's a mechanical spring, and where you store elastic energy. That's an application for those materials. So the applications often originate from several other properties beyond the elasticity, right? So they're very high strengths, very high elasticity. The strength is on the order of 2 to 4 times this of really good steels, right?
We're like gigapascals. These things are impressive.
Gigapascals, right? Elasticity is often even more, right? Like 3 to 7 times of the materials you're used to, right? Then things become a little. So then people, when they early on looked at these materials, they always looked at the stress strain curve, right? Where you characterize them, let's say in uniaxial, you pull them or you push them, and they said, well, but they have no ductility. Right? These materials are brittle, because that's how every engineer, let's say if you're an aerospace engineer and somebody comes with a new material, the first thing they ask, show me the stress strain curve, what's the ductility, right? Yield strength and ductility. So that has caused a lot of confusion. And probably in the last 10, 15 years, people have really focused on this and observed that the fracture toughness, which is what people associate with ductility in crystalline materials. And it is very, very strongly correlated to in crystalline materials. The ductility, which is absent in metallic glasses, yet they can have a very, very high fracture toughness. Right?
Dude, upper end of 50 megapascal root meters. That's like at the lower end of steels. That's crazy good.
Yeah. In fact, the most common one goes up to over 100 megapascal root meter.
Oh, is that right? Wow. That's not one of the vitraloids, is it?
Yeah, it is. Zirconium-based, right? So these are, let's say, the front runners, right? But very practical materials, right? And this has caused a lot of confusion, right? Because it's counterintuitive.
Yeah, because look, it behaves a lot like a ceramic, right? These materials, in terms of their strength and their lack of ductility, it's looking like a ceramic. But where those things have a fracture toughness of less than 10 typically, this thing is 10 times that. That's really something that's breaking the rules.
Yes, and this has caused, again, this is really just understood in the last few years, right? How can a material lack any compressive or tensile uniaxial plasticity, yet can be so tough, right? So tough, the energy you put in, or in fracture toughness, the energy you put in if you already have a crack in the material. This is very different from crystalline materials, and it's still, very confusing.
This is like an open area of research, then, you're saying?
It's almost an open area of research. I think it is better understood now. And the short answer, we would have to talk about shear bands, right? Then this kind of explains how this very schizophrenic behavior is possible that we are trained not to expect.
So why don't you describe shear bands? Because, when I was reading some of these papers that you recommended we dig into at a time, that's not a term that I don't teach mechanics, right? And so if it's not showing up in an introductory material science course, I don't really know much about it. So tell us about shear bands. As I understand it, they're regions of local deformation, plastic deformation, but why are these the mechanism whereby you get deformation in these materials as opposed to anything else? I get it, there's no dislocations, but what are shear bands?
Yeah. So shear bands, let's first say if you pull your sample and you carry out a stress strain curve measurement. So you pull your sample and you load it, and then the atomic bonds, they stretch, right? It's elastic, go to very impressive high stresses up. And then at some point, somewhere in your sample, by a tiny amount, there's a weak link, right? There's a slightly smaller cross-section, right? It might be just by one atom, right? The cross-section is thinner. So this is the cross-section that experienced the highest stress at first, right? And so now in this cross-section, when you reach the yield strengths of these materials, these very impressive high yield strengths, right? This is the one that feeds at first. And so in this cross-section, atoms, they start to kind of rearrange, move around a little bit, right? And give in to the stress that they experience, right? And the main stress is the shear stress, so that defines the direction. They give in to this stress and rearrange. And when they rearrange, they generate some heat already, right? So it becomes slightly warmer, first warmer, then hotter. The material becomes even softer, right?
But locally.
So in this region where they start to rearrange, and this plane becomes softer, right? And because it becomes softer, all the deformation is further localized in this region, and it becomes even softer. It runs into this instability. It's the extreme case, and it's very, very similar to, close to this extreme case. You have two rigid parts that don't deform at all plastically, and one,
the region between them, right?
Only that one region in between carries all the plasticity, right? And that's very dramatic.
That's very cool.
It's very, very dramatic, right? So those shear bands itself, if you can stop them, they are not, they essentially don't hurt the mechanical properties. So you can have a metallic glass that has a lot of shear bands, and it would still behave very strong, right? Very impressive mechanical properties. But the problem is that they become very quickly unstable, and then they become so soft, they essentially, it's almost like a liquid film in between.
Becomes a fracture, right?
And then they just fracture, right? So what people first observed was if they bend the sample, the stress is very large on the surface, and it drops towards the center. It goes to zero.
Yeah, right.
And if you make the sample thinner and thinner, then the stress drops over a smaller and smaller area. So if you make a sample thin enough, BMG, you can bend it, you form these shear bands, and they travel towards the center of the sample, but then they run out of steam because the stress goes to zero, right? So
because your compression on one side, tension on the other, so you've got the zero
exactly.
in the middle.
They have no motivation to go any further. So now and that's the understanding that we now have, if the stress drops quicker than the shear band softens, then you can deform these materials plastically. You have ductility in these samples, right? But if you so the stress drops quicker. It starts on the surface, upon bending, high stress, and goes to zero in the center. And if this happens over a small area, and if that is quicker, then it takes the shear band to develop its full instability, to become hotter and hotter and hotter and lose all its strength and breaks. Then you can prevent it. Then you can form these shear bands. And this is the only way you can plastically deform metallic glasses.
This is kind of ironic because we've gone from the point where, heck, you can cool these things slowly, therefore you can make big samples, but you're telling me that if you want the amazing properties, the plasticity, you got to go back thin again.
That is true. Yep, that is true. It's not ironic, but if you look into all applications, everything they're used for is essentially thin. And in fact, if you look around your room and you look into most metals that we use, at least higher performance metals,
interconnects, things like that.
Everything is thin, right? I look at computer casings, right? Cell phone casings, right? Eyewear, everything.
Maybe a millimeter, yeah.
Exactly, right? So in these dimensions, they are very ductile. It is ironic, yes.
Yeah.
One question I had is, even though you're cooling things down and we don't see grains and other heterogeneities that we would expect with a crystalline material, not all liquids and the arrangement of those atoms are going to be uniform either. Are there heterogeneities that arise from the cooling process? Or I guess are all cooling processes equal? Or is there still benefit to going faster even when we have more time?
That's a very difficult question to answer, right? And as I said, the liquid state all these things have been solved 150 years, right, and explained by Gibbs and others, right? In the solid state, we know all this, right? In the liquid state, in fact, this is what people really just learned in the last 50 plus years, that we envision a liquid with all these atoms. We look at this and say, this is a completely random mixture. Of course it is random mixture, has or we envision it to have high entropy in our head. It's also a misconception. But if you actually look into these liquids, right, they do still form not random mixtures of these elements. They form predominantly a chemical, but also somehow a topological order. I believe the chemical is the driving one. So gold still likes silicon a lot, right, in its liquid phase. And if it can, it surrounds itself with silicon, right, and not in a random way, whatever is next to it. By if you count the gold, you see significantly more gold-silicon bonds in the early example. So there is a lot of ordering in these liquids. We think of liquids as being this just atoms. They are randomly distributed in like kind of random spots. The only thing we know, locations, the only thing we know is that they have a certain density that we macroscopically measure, right? But they are highly not random, and that it has been a great shocker to the study of liquids and certainly the study of metallic glasses.
Yeah, I was going to follow on that. So in looking at some of the papers you sent, a lot of them are pointing out that, when you do look in closely, there does seem to be some, even if it's not a secondary phase, there is some segregation and local concentration disorder without the material. It's not evenly distributed everywhere. There is some segregation, it looks like, in these materials.
Yes.
Okay.
Yes. Chemical segregation, yes. They are not periodic, right? Clearly not periodic.
Yeah.
Right?
And yet something, right?
Yeah.
There's some degree of not perfectly random like you'd expect out of the strict definition of like amorphous, right?
Mm.
One of the things I thought was really cool about this when I was learning about it is, I'd always learned about the TTT diagrams, and I never actually knew how they made them. I sort of figured it was trial and error, like, well, we tried it at this rate, and we didn't see whatever phase form. But here they talk about a really cool way where they've got this levitating furnace, and you've got a pyrometer measuring it, and essentially when the secondary phase forms, there's an enthalpic change that causes the material to heat up. And so by monitoring the temperature, you can actually see, as a function of time, with the pyrometer set on it, the onset of crystallization. And from that, you can actually construct the TTT diagrams, which was, for somebody like me, I never knew where they came from. And here's a way you can actually measure it pretty accurately.
Yeah, so they are they're measured in exactly this way, right? So you take a liquid, and then if you cool the liquid below its melting temperature, it contains heat, right? If you let it crystallize, that's the so-called recoalescence. So that's the stored heat in the liquid. And so now if you, let's say, go below the melting temperature and then you keep it there and watch it, and at some point, right, then the atoms, they fluctuate around, and at some point they overcome the activation barrier. They form a nuclei. This nuclei then takes over, crystallizes the sample, and it releases that heat that can be also relatively precisely calculated how much heat this is. It's well understood, and then you can notice this. You can often see it with your naked eye, right? These flashes, and then you mark a data point there, right?
Pretty rad.
Yeah.
And obviously, if you can do this just to measure the property, it stands to reason that once you make your sample, right, you've quenched it sufficiently fast, so you've got now bulk metallic glass. It does limit its high temperature use, right? Because there is still that kinetic limitation to a thermodynamic driving force to make it crystallize. So if you heat this thing up, time and temperature are sufficient, it will crystallize. You will lose the properties of the BMG as it crystallizes into other phases, right?
Yes, that is exactly the case. So if you heat it up, it's highly metastable, right? It really wants to crystallize. And if you give it enough time, so now what you do is if you heat it up, let's say you cooled it with 1 Kelvin per second, and now you heat it back up. With 1 Kelvin per second, you avoided crystallization. Now you heat it back up, and you leave it there for more than 1 Kelvin at some temperature. Then it starts to crystallize. then you run into this nose, right? And it crystallizes.
Yeah.
But looking through the literature, it seems that if you're really careful and you're really fast, you can heat it up a little bit, just enough to make it soft that you can deform it. Is that right?
Yes. And that is the true, to me, this is the true novelty of these materials. And this is what kind of brings together the two major material classes that have kind of carried economic growth, carried cultural growth and all this in our societies, polymers and metals in the last 200 or so years, right? And brings them together. And let me just say a few words about these two different material classes, right? So metals are of course fantastic, right? Everything we have fantastic properties. Everything we build to last, right? With safety and all this, we like to use metals and we don't like to use thermoplasts. The problem with metals is they are extremely difficult to make anything out of this, to process them. And it's shocking. We are just so used to it. We can just make them into some sheets, right? We can make them into pallets. We can pull wires, right? But if you take a random object on your table, these are all the things we use, you can never really make this out of a one-piece metal, right? So if you want to make it out of a one-piece metal, you have to join it, you have to machine it, right? You have to do these kind of things, right? Even an additive, right? So if you look into additive manufacturing, right, of thermoplast, it's a trivial thing these days, right? You can buy a $200 printer and print wonderful things. If you want to do it with a metal, that's a different beast, right? It's like 1,000 times more expensive, and you need it's very, very difficult, right? But we do like metals. Thermoplastics, on the other side, you can shape them into anything you can imagine. If you've ever seen how a soda bottle is made
it's wild.
It's absolutely amazing, right? But of course, right, they have bad mechanical properties. They disappoint us. We don't use them for structural applications, right? I'm only talking about thermoplasts, right? So the absolutely outstanding property about metallic glasses is that we talked about their room temperature properties that even exceed those of the best metals. And if it comes to processing now, they can almost be processed in the same way as thermoplasts are processed. Exactly what you said, Andrew, that you can take them and heat them back. So you cool them to room temperature. Now you have a simple shape, a disc or something, and now you can heat it up, right, into this. You avoid this TTT diagram. You heat it up, and then once you're in this temperature region, you can deform them. And if you want to deform them at lower force, you go even a little higher. The time shortens. But so the time windows are very practical. You have about minutes, and you can deform them easily with very little forces by 10,000%. Right? So you can do the same thing. In fact, we have demonstrated this. You can blow mold them into like shapes.
For real? I've never seen that. That's
water
awesome.
bottles. We've done a Chanel No. 5 bottle, right? And into those objects, you can do this within a few tenths of seconds, and into shapes that you have never imagined a metal can be in, including additive manufacturing. Right? So that's the true kind of breakthrough of these materials. And that's what commercially makes them extremely interesting, right? Because you can now combine the ease of processing with metallic properties. And that's the really breakthrough.
So maybe to pivot a little bit, this is really fantastic, but impurities exist. And if all of a sudden you think you have, gold and silicon, and then there's some oxygen in there, does that cause problems? All of a sudden there might be secondary phases that could form. All of a sudden you might nucleate something a lot quicker than you intended. How are those? How big of an impact do those have, and how are they dealing with them?
Yeah, that's more than a serious problem, right? And it is in some alloys more than in others. So that also where the research community has been focused on for many years, right? So in some cases, it can be really extreme, So the smallest amount of oxygen in there can essentially change all the mechanical properties, right? Can just crystallize it, right, and so on. And of course, a lot of research has been done, right, to do this, right? So to remind you of steels, right, that's why they put manganese into steels. I learned this from your podcast, right? You put manganese into steel to scavenge the sulfur, right, which otherwise would cause a lot of problems. And so there are similar strategies. We, for example, use yttrium to add into the alloy, and yttrium likes oxygen a lot more than zirconium, titanium, nickel, copper, and all these other elements. So that is a very, very valuable strategy.
Is it removed like a flux, or is it actually incorporated into the final structure as a secondary phase?
So the yttrium is not removed. The yttrium oxide is just, floats on the surface, so it can be subsequently removed in a casting process. You take it out. There's also fluxes, right? The most common one is boron oxide. So in fact, this is when we developed these ridiculous, where I said you can keep it 100 seconds at 1 degree. So the cooling rates are incredibly slow, right? So that's why these strategies, they are very, very sensitive to impurities, right? And this is where we now go this long way that the conventional metallurgy industry have been doing for more than 100 years, right? Like trying to get all these harmful things, you develop strategies to make them less harmful, right?
Well, this has been fascinating. I do have one final question, and then we can set up what I think will be a future conversation. The first one is, we just did an episode on high entropy alloys, which people were wild about, and it's been fascinating to dive into that field where a lot of the same things are there. The same things that you're looking for that can cause a frustration of the lattice and therefore a slow kinetic transformation are the same things that give rise to these so-called high entropy alloys, right? And in fact, one of the main reasons why we like high entropy alloys, and one of the things that shock the world, is that they form a single phase with really high solubility limits that nobody sort of expected. But you can also form amorphous high entropy alloys, right? Sometimes they don't form the phase at all. There are this class of amorphous high entropy alloys. So are these just bulk metallic glasses? Are these different? Have you given much thought to this? I was kind of curious what your perspective on those were.
Yeah. First of all, entropy is not the issue. It's not the issue in the high entropy alloys, and it's not the configuration entropy.
Even like high alloy steels are like comparable entropy, right?
Yes. And actually, so in metallic glasses, this was one of the shockers, right? When you actually measure the entropy, the configuration entropy, it is very, very low. It's particularly low. And this goes back to Andrew's question about the liquid. So the liquid orders so much, it takes away the enthalpic or enthalpy or chemistry always seem to win, right? You cannot beat it with entropy as we thought in the early days of high entropy alloys, right? This is the name is just stuck with us, right? So entropy is not the issue. So then they just call these metallic glasses that have a lot of like elements at similar composition, right? They call them high entropy amorphous alloys, right? But it has really nothing to do with entropy. Certainly not in the metallic glasses. I will not say more about the high entropy alloys, but certainly not within the metallic glasses, right? So,
but maybe my question is, are they inspiring new directions for where to find bulk metallic glasses now that they're finding essentially amorphous solids in regions where we wouldn't have expected to have found them?
I would say the most successful way to find metallic glasses, right, is the strategy that what you said early on, Taylor, that you look into these deep eutectics, right? Of course, for gold silicon, we just open the phase diagram book, and there they are. But if you have a 4 or 5 component system, you have no idea.
Show me that diagram.
Show me that diagram, right? So if you find these very, very stable liquids, right, And there's a very, very, very good chance, right? The correlation is very, very strong that the best metallic glasses are there. So the focus is really on understanding where do you have these deep eutectics, right, to find new metallic glasses. And they are, to some extent, there is some independency about the atomic sizes, right? The atomic sizes, they dominate, or they also dominate the kinetics. You have a big atom, medium-sized atom, and small atoms. You can pack things more efficiently together. You have a higher viscosity. Things move slower. So the combination of those two things really guide the development of new metallic glasses, right? And of course, the challenge is the space they live in, metallic glasses or alloys, right? This is also, you can estimate this somehow, is vast, right? By some measurement, it can be 10 to the 12 alloys in 5-component system if you take the 50 most practical elements. So
That's a lot.
It's a lot, and the technique is too slow. So then what people have been doing more and more is doing high throughput experiments, right, where you can do 1,000 alloys in a day, right, high throughput characterization. And of course, we have all looked into machine learning strategies, right, and combining even those strategies with automated machines, right, where we can do active learning and this so forth.
So we are excited to continue that conversation in the very near future to hear about what that process actually looks like for bulk metallic glasses. Jan, this was a killer episode. Thanks so much for joining us today. I learned a lot. We appreciate your expertise.
Awesome. Thank you.
Okay, that was a fantastic episode, and we are super grateful that Jan was able to join us. Now, obviously, Jan's at Yale University, but at the end of our conversation, we talked about how are we going to find new materials going forward. And to that end, he is also associated with a cool new startup in the space called Radical AI. And we will for sure be doing some future episodes with them where you can learn more about that. But for now, let me tell you a little bit about Radical AI because they sponsored this episode. Radical AI is focused on changing the way materials are designed, developed, and discovered through the integration of artificial intelligence, engineering, material science, and applied research. Their goal is to build full-stack solutions from AI-generated materials all the way to autonomous, high-throughput experimentation. That gives you a bit of a teaser of what we're going to talk about. So we are super grateful for them.
The Materialism podcast is also sponsored by Materials Today. You can visit materialstoday.com to stay up to date on the latest happenings in the material science field and read some of their fantastic articles. You can also head over to elsevier.com to find out more about their journals, books, conferences, and related programs. As always, thank you for listening to this episode of the Materialism podcast. If you have questions or feedback, please send us emails at materialism.podcast@gmail.com. Make sure you subscribe to the show on iTunes or Spotify or wherever you listen to your podcasts. And if you like the show and want to help us reach more people, consider leaving a review. It helps us improve and it exposes the show to new people. Finally, you can check out our Instagram page at materialism.podcast to connect with us, see some of the cool art we make for the episodes, and let us know what new material you'd like to hear about next. Lastly, we'd like to give a shout out to Alphabot and Kolobyte for making the music for the podcast. They both make a ton of really cool synthwave music, so go check them out on Spotify. Catch you next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.